Hey guys, how are you doing? In this video, I'm gonna give you a brief introduction of Markov decision process, MDP. If you Google yourself, probably there's a lot of tutorials and definitions out there, but I think many of them are quite hard to understand. So I just want to put it in a simpler and more straightforward and intuitive way. I'm not jumping directly into all those math equations and symbols out there. Just give you a simple example here. This example here is from the lecture from UC Berkeley. Unfortunately, this video is kind of long, more than 1 hour. Well, if you have enough time, you can maybe watch the full video from here. But I just want to use this example here to explain the problem. Now, let's say you have a car, and your car could be in one of these three states: cool, warm, and overheated. Now, you have several choices when you're driving the car. You can either drive it slow or drive it fast. So there's one goal you want to reach, which is travel the car as quickly and as far as possible. Well, when I say that, I'm not giving you a very formal definition in math sense, but I'll give you that math definition later. Now just remember, you could be in either of these three states, and you can choose to drive slow or drive fast. And when you do drive slow or drive fast in any of these states, there's a probability of the car transition to another state. For example, if your car is cool now, and if you drive slow, then there's 100% that the car is gonna keep cool. And if the car is in warm state and you drive slow, and there's 50% probability that it's gonna turn cool, and 50% probability that it's gonna keep warm. And if you drive fast when the car is warm, then there's 100% probability the car is gonna be overheated here. Now think about the process. Transitions can be taken from from cool state to warm state, and warm state to cool state, and warm state to overheated state, right? But whenever it reaches the overheated states, then it stops. It cannot jump back to warm state or cool state. So that means everything is over. So if we list out the transition sequence, it could be cool, warm, and then finally overheated, right? So let's say for one possible sequence, like slow, warm, overheated. So for each one of the transition we take, we get a reward or punishment. So for example, here, if we transit from cool to warm here, using the fast action, we got a +2 reward. And for the opposite, if we transit from warm to cool state, then we got a +1 score reward, right? And here, if we transit from warm to overheated state, which is very bad, we get a -10 reward, which is a punishment actually. So everything just ends. So if we sum all those rewards together, we get a total score, right? So that means for every list of transitions, we can calculate a total reward. So with that score in mind, we can define the optimization problem itself, right? When we talk about an optimization problem, let's say, for example, for the simple equation here, y equals power of x. If I ask you, what is the max value of y? Probably you'll know that there's no answer for this question, right? But if I give you one more constraint, x is within range -2 to 8, then I think it's quite straightforward that you will know the answer, right? The maximum value would be 64, right? So that's because we have a constraint and we have a goal. The goal is to maximize y, and the constraint is x within a certain range. And this is a quite simple problem because the problem is also deterministic, which means given a specific value x, you're 100% sure what's y gonna be. But for this problem here, you can't say, if I choose to drive slow, then I'm 100% sure what's the next state the car is gonna be, right? So it's a probability problem here. So if this is a probability problem here, what can we expect to optimize? Yes, of course there is something we can optimize, which is the expectation. Let's say for each transition it takes, there's a reward or punishment, and we add all those rewards together, and we have a score, right? So we want to maximize that score. Since you cannot, deterministically maximize that score, but you can still maximize the expectation of that score, right? So the problem here is you can control something, which is you can choose to drive slow or drive fast, and there's something you cannot control, which is the probability of the transition. So this is the very important part of this MDP problem. So now let me give you a formal definition of what a Markov decision process is. So the formal definition here is a Markov decision process is a 5-tuple of these things. And these things are, let me give them one by one. S is a finite set of states, which means, these kind of things, cool, warm, overheated, they're states. You can be either one of these 3 states here for this problem. And A is a finite set of actions. So when coming to this problem, the actions you can take are drive slow or drive fast. Yeah, only 2 actions here. And this is the probability that action A is A in state S at time t will lead to state S prime at time t plus 1. What does that mean? If you're in a state warm and you choose to take action of driving slow, then you have the probability of turning the car into a cool state, 50%. And also 50% probability to keep the car in a warm state here. Well, so that's the conditional probability. Well, I think you understand this conditional probability if you learn the probabilities and statistics. And this function here is a reward function, I would say. If you transition from state S to state S prime, then you'll get a reward. Of course, the reward could be either positive or negative. Let's say in this example, if you turn your car into an overheated state, then you get a punishment, -10. And gamma here is the discount factor, which represents the difference in importance between future rewards and present rewards. But just to give you a simple definition, I think we can ignore the gamma here. As for how to solve this problem is without the scope of this video, but I can tell you that usually this kind of problem is solved by dynamic programming. So let me restate this problem here. The key thing is you have a goal, maximize the expectation of the sum of rewards, and the constraint is the conditional probability of being in a certain state and being in a certain state and choose to take an action. Well, one last question is how do we represent the answer? For this simple problem here, we just give the x value, which maximize the y value, right? But for this problem here, it's things are a little bit more complicated. Well, actually, the answer we want is a map. A map of what? When we talk about a map, we usually mean a key and a value. So the map we want here is a map that has a key of the state, for example, warm, and the action we take, for example, slow or fast. Let me give you one instance of the map here. Cool state. The first column is the state, and the second column is the action you take. Let's say, for example, slow, warm, and fast. Oh, okay, this is one combination of the map. Another combination could be cool, fast, warm, slow, right? And there could be some other combinations. But for each combination, you will get a score of the, expectation of the rewards, right? So let's say this is policy 1. Whenever we're in cool state, we drive slow. Whenever we're in warm state, we drive fast. And policy 2 here. Whenever we're in cool state, we drive fast. Whenever we're in warm state, we drive slow. And there could be, policy 3, policy n, right? So for every policy, we can, we can calculate the expectation of the rewards, right? Correct? Although we cannot deterministically predict the whole process, the whole transition sequence, but we can know the expectation of the rewards. Am I correct? So if I'm correct, then that means we can compare every 2 of the policies here, listed here, right? So if we can compare every 2 of the policies among all the possible policies, then there must be one best or optimized policy, right? So that is the policy we want. So remember, the optimized policy we want is a map of action we take when we are in certain state for every state, every one of the state. Okay, now one final question. Why is this process called Markov? Well, if you don't know what Markov property is, then you can take a look at this definition from Wikipedia. A stochastic process has the Markov property if the conditional probability distribution of future states of the process, conditional on both past and present states, depends only upon the present state and not on the sequence of events that preceded it. A process with this property is called a Markov process. Well, if you still think it's hard to understand, then just take a look at this again. So let's say, for example, if you're in a warm state, try to think about it. Is it important how you come to this warm state? Whether you come from cool state to warm state or come from warm state itself? It's not that important, right? Because whenever you are in a warm state, there's always a best strategy for you to choose whether to drive slow or drive fast. The best strategy taken forward, has nothing to do with the previous state, whether it's cool or warm, right? Correct? So that means when calculating the optimized reward score, what's important is the current state, not the previous state, not on the sequence of events that preceded it. Correct? So this is a problem that has Markov properties. So that's why we call it Markov decision process. Okay, thank you. See you next time.